In Chapter 6, we're looking at gases. Gases behave in a very regular way. The behavior of gases is so regular that our Kelvin temperature scale was based on the shrinking volume of gases as temperature is decreased. And we know that you cannot have zero volume of matter, and so we have theorized that the lowest possible temperature that you could have would be at nearly zero volume, and that's what zero in the Kelvin scale is based on. We examine the properties of gases by using what we call the kinetic molecular theory. The kinetic molecular theory states that gases are rapidly moving, bing-banging around and bumping into each other, and that the size of those gas particles is so small that we actually consider the volume of gas particles to be zero in our calculations. Of course, that's under ideal conditions, and if under real conditions, gas molecules actually do have volume, but when we're doing calculations and considering the gas to behave what we consider ideally, then we consider the gas to have no volume, and also for the gases to have no attractive forces between each other. Something to remember is that the movement of molecules, including gases, is faster as the temperature increases. So as the temperature increases, the kinetic energy of gas molecules also increases and they move faster. All right, now the first thing we're going to look at is gas pressure. Gas molecules are moving around, and as they move around, they collide with things. That collision is a force. The sum of all those gas particles colliding with something actually causes our pressure. That force of their collision is the pressure. We measure this pressure with several different types of units. The units that we're going to be actually using are going to be atmospheres, millimeters of mercury, and torr. PSI is a pressure, but that is an English method of pressure. PSI stands for pounds per square inch, and we do not use pounds per square inch anymore. Torr and millimeter are used, and so are atmospheres. There's also something called pascals and kilopascals, but those are not used that much by chemists. That is another way of measuring pressure, but usually physicists use pressure in pascals. 1 atmosphere is about what we're experiencing from the atmosphere around us right now. Now, this is not talking about the atmosphere. This atmosphere right here, 1 atmosphere, is not really truly the atmosphere. This is a unit of pressure. 1 atmosphere as a unit, 1 atmosphere is equal to 760 millimeters of mercury and is equal to 760 torr. A torr and a millimeter of mercury are identical, just like a centimeter cubed and a milliliter are identical. They're just the same unit, but with different names. You do need to remember that 760 millimeters of mercury or a torr is equal to 1 atmosphere because we will be using those relatively frequently. There are several gas laws that we're going to look at. The first one is Boyle's law, and Boyle's law can be summarized very easily and say that basically pressure and volume are inversely proportional to each other. And we can write it as P times V is equal to K. And we can write it this way, which is P1 times V1 is equal to P2 times V2. This means that when I multiply pressure times volume and then I make a change to one of those, pressure or volume, what happens is the other one must change too. That's what proportional means. So inversely proportional means that when pressure goes up, volume must go down. And this is expressed in this equation given at the bottom of this PowerPoint here. Now, you can see a picture of this up above is that if the pressure is 1 atmosphere and the volume is 2 liters, when I double the pressure to 2 atmospheres, the volume goes down to 1 atmosphere. And you can see that 1 atmosphere times 2 liters is equal to 2 atmospheres times 1 liter. The product of 1 times 2 is 2 in both cases. So this is a picture of what happens, and this is a formula for what happens, and that's called Boyle's law. There's Charles' law, in which we say volume and temperature are proportional. What that means is that as temperature increases, so does volume. And we can write this little equation, volume over temperature is equal to K, a constant, if we want. But it's much easier to look at it this way. Volume 1 over temperature 1 is equal to volume 2 over temperature 2, or volume divided by temperature is equal to volume divided by temperature at new conditions. And I can look at how this happens if I have a volume of 1 liter on the left and a temperature at 200 Kelvin. If I increase my temperature to 400 Kelvin, well, my volume is going to increase by 2 also. I doubled my temperature, so my volume must double. Notice the temperature is in Kelvin. This does not hold when we use Celsius. When dealing with the gas laws, we always have to use Kelvin because our gas laws are derived from that. There's no linear relationship in these equations unless we're using Kelvin. And you need to remember to go from Kelvin to Celsius. How do we do that? To go from Kelvin to Celsius, we subtract out 273.15, and to go from Celsius to Kelvin, we add 273.15. That was back from chapter 1. Charles' law we see happening all the time in our weather, because as the sun heats up air, it expands. Expanded air is less dense, so it rises. Then it moves up. As it moves up, it can cool down. When cooling down, it compresses its volume, and so then it's more dense and it sinks. And that's how we get a lot of the currents occurring in our atmosphere, and why we have air pressure differences causing wind. Gay-Lussac's law is another law, and that is pressure and temperature are proportional to each other. That means as pressure increases, temperature increases, or as temperature increases, pressure increases. Pressure divided by temperature is equal to a constant. Again, temperature must be in Kelvin. We can express it much more an easier way to look at it as initial pressure over initial temperature is equal to final pressure over final temperature, or we can say, again, pressure divided by temperature is a constant. This means if I double my temperature and my volume is held constant, then my pressure will double. There's one more law called Avogadro's law, and that is that volume and number of gas molecules is proportional. That means that if I double my number of gas molecules and all of the other variables are held constant, my volume will double. We can express that same relationship this one way. Initial volume over initial number of moles is equal to final volume over final number of moles. And I can see it happening in this picture here, that when I have 1 mole occupying 1 liter, if I double my number of moles, well then my volume doubles. Avogadro's law is often used to give us what we call a standard molar volume. At standard temperature and pressure, which is considered to be 1 atmosphere and 0 degrees Celsius, or we can say 760 millimeters of mercury, that's the same thing as 1 atmosphere, or 273 Kelvin, which is the same thing as 0 degrees Celsius. At standard temperature and pressure, what we find is 1 mole of any gas. Of course, that's a gas that's not near the point of liquefaction, but 1 mole of any gas will have a volume of 22.4 liters. This is called the standard molar volume, and so basically 1 mole is equal to 22.4 liters of volume when we have 0 degrees Celsius and 1 atmosphere. If we have 1 mole of nitrogen and 1 mole of helium and we put them both in a balloon at 1 atmosphere and 0 degrees Celsius, we will find there is 1 mole of those particles. It doesn't matter that one is nitrogen and one is helium. As long as you have the same number of particles and they are experiencing the same temperature and pressure, the number of particles is going to be the same. Notice, 1 mole of nitrogen is 28 grams. 1 mole of helium is 4 grams. That means that the density of nitrogen is much greater. It's going to be 28 divided by 22.4 liters, which is, I'm calculating it right now, 1.25 grams per liter. Whereas for helium would be, the density would be 4 divided by 22.4, which would give you 0.18 grams per liter. And from those densities, you can see why a balloon full of helium will rise in the atmosphere and a balloon full of nitrogen will not rise. It actually sinks because the balloon material has greater density than that of nitrogen. So remember this little relationship that 1 mole of any gas at SDP is going to be 22.4 liters. How can we use this? We can use this in many problems. For instance, right here it says how many moles are contained in 2 liters of nitrogen at standard temperature and pressure. The given in the problem is 2 liters. From our understanding of standard molar volume, we know at SDP 1 mole is equal to 22.4 liter. So we can write a conversion factor for mole to liter or liter to mole for this gas. Now remember, this is only with gases. It does not apply with liquids, nor does it apply with solids. Because I have liter as my unit and I want to go to mole, I need to choose this fraction in order to do my conversion. So I take this fraction and set it up so that liters cancels out and we go to mole, and then we know how many moles we have. All those gas laws may have you quite concerned, thinking there's so much to remember here. But there really isn't very much to remember, because all of those gas laws that we've just looked at can be combined into one equation that we call the combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. If any one of these, or even 2 of these, variables are held constant, well, then they drop out of the equation. For instance, if the number of moles and the temperature are held constant, then N1 and T1 and N2 and T2 drop out of this equation, and you get P1V1 equals P2V2. That's Boyle's law. If you look back in your slides, you'll see that matches Boyle's law. If, for instance, instead that you have volume and number of moles being held constant, then V1, N1, V2, and N2 drop out of this equation. The resulting equation is P1 over T1 equals P2 over T2, and that's Gay-Lussac's law. So just remember, you need to know this and the standard molar volume and how the various pressure units relate to each other, and that's about it in what you need to remember for everything that we've covered so far. Do remember, though, when looking at this equation, when conditions are held constant for one variable, drop it out of the equation.